If you recall, yesterday we thought about this problem a little bit where I have a vector field and I want to calculate the flux of the vector field through this rectangle. This is a variation on the problem where we had water flowing through a cylinder. And I want to highlight the differences between the thinking that we had on that cylinder problem and the thinking that we're going to end up with on this problem. So why we put these two problems together. There was some kind of committee that put these problems together. So first, let's take a look at, let's remind ourselves of the cylinder problem just briefly, the highlights of the cylinder problem. So if you would recall, in the cylinder problem, what we had was water flowing through a cylinder at a constant rate. And we measured the flux as the water flowed through a circle and an ellipse. So the area of that circle was 4 pi. And when we angled this off to an ellipse, the area of that ellipse was 4 pi times the secant of theta, where theta is the angle with the vertical. Regardless of how we calculate the flux through the as the flow through the circle or the flow through the ellipse, the volume of water going through the pipe needed to remain constant. So in both cases, the water was flowing at 3 centimeters per second. But in both cases, the flux needed to be 12 pi. So in this first calculation, the flux, we calculated the flux to be 12 pi cubic centimeters per second. So the flux is calculated through the cylinder. We'll take the speed of the water, which is 3, and multiply by the area, which is 4 pi. In this case, we just had to multiply the 3 times the 4 pi to get the 12 pi cubic centimeters per second, because all of the 3 was flowing perpendicular through the circle. So all of the 3 is perpendicular to the circle. The angle between the velocity and the normal vector of the circle is 0. So the cosine of 0 is 1. 3 is perpendicular to the circle. So the angle between the velocity and the normal vector of the circle is 0. And the cosine of 0 degrees is 1. So I take 100% of that velocity flowing perpendicular through the circle. And so we get 12 pi. The flux through the ellipse should be calculated the same way. We're going to take the velocity, multiply by the area. But we still need to come up with 12 pi. The area has increased, but the velocity flowing perpendicular through the area is decreased by, in this case, a proportional amount. So the flux through the ellipse is not going to be 3, I'm going to need the amount of the flux perpendicular to the surface. This is the idea behind a flux integral. This is the idea behind a dot product. We're not just multiplying the velocity times the normal vector representing the area, unless they're just going in the same direction. In single variable calculus, when our multiplication just gets to be scalar multiplication, the angle between our quantities is just 0, because the cosine of 0 is 1. We just get all of it. But here, we're not getting 3 flowing perpendicular through that ellipse. We're getting 3 times the cosine of theta flowing perpendicular through the ellipse. So I'll need 3 cosine theta. That's the velocity perpendicular through the ellipse. And then we'll multiply that by the area, which has increased by a proportional amount, 4 pi times the secant of theta. The volume of water going through the pipe is not going to change because of how we measure it. This is the speed of the water flowing perpendicular through the surface. Oh, to the ellipse, excuse me, not surface. That's the speed of the water that's perpendicular to the ellipse. That is the component of the velocity that's in the same direction, or that's that's in the same direction as the normal vector for the surface. That's the component of the 3 that's in the same direction that's normal to the ellipse. In this problem, the area increased, and so we're looking at less velocity. Because in the cylinder problem, the flux, the volume of water going through the pipe needed to remain constant. Correct. In the new problem that we had yesterday, the flux was not constant. The area was constant. So what we did was instead of have this 12 pi, the flux be constant, we fixed the area as constant. The area was a constant 10. Because I put it at an angle of, or a slope of delta z over delta y 4/3. Also, we started the problem here in the middle rather than giving you the flat problem first. So in the, yes. Those 2 thetas are the same angle, yes. Any questions? Right. What we could think of doing is grabbing this angle here between the 3 and the 3 cosine theta and kind of like turning it 90 degrees downward and then moving it up to the top. I think yesterday I did some stuff with parallel lines and alternate interior angles. And then after class, my call. I'm sure everybody in the room was like, oh. that one guy's gonna make a video. It's gonna be like, oh. Then I have to make a response. And it's like my job to overcomplicate things. That's not my job to overcomplicate things. It's just my habit to overcomplicate things. I don't know. So in the rectangle problem, so in the cylindrical problem, flux remained constant. Flux remained constant. The area increased, and we lost some velocity through the surface due to the angle. In the rectangular plate problem, area is constant. We will still lose some velocity from the angle. We'll still lose some velocity as we have to find the component perpendicular to the rectangle, and so flux will decrease. So in the cylinder problem, the flux was constant, area increased and we lost some velocity due to the angle. In the rectangle problem, the area is constant. We lose some velocity as we go perpendicular through the surface. So that means our flux is also going to decrease. The idea, go ahead. Correct. So let's think our way through that problem. So yesterday, my recommendation was to think of the problem as a simpler version of the problem. If I lay the rectangle flat, on the XY plane, here's a side view. There, the area is 10. There, the area is 10. And we started off with a constant velocity of 1. I really could have reused the 2 at this point, but I just went with 1. I wrote a vector, so I'll say it's 1K. So in this case, the velocity is going perpendicular to the normal vector. Normal, if I lay the plane flat, there's our normal vector. So all of the vector field is going through the area 100% because the angle between the normal vector and the velocity is 0. And the cosine of 0 is 1. So we are getting 100% of that velocity going perpendicular to the surface. 100% of that velocity is going in the same direction as the normal vector. So if we want the flux, we just multiply. I'll just take my velocity of 1 and multiply by my area of 10. and we'll get 10. Y'all should be immediately suspicious about what I wrote here, because flux is a dot product of the velocity vector dot the area vector. And I just wrote like times 1, the scalar, times 10, the scalar. What did I not write here? Cosine of 0. So. Oh. Because this is how we calculate the dot product. Magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. So the cosine of 0 equals, that equals 1 is the part that I didn't write here. So that's the part that I didn't say yesterday. But we'll get to the second problem. We still have to angle up our plates. Right. Now, this is how we calculated the dot product here by saying the magnitude of V times the magnitude of A times the cosine of the angle between them. That's how we calculated V dot A in this case. By product of the angles multiplied by the cosine of the angle between them. And when I say A, that vector A, the magnitude is the area and the direction is normal. I wrote the area as a vector. That means it has to have a magnitude and a direction. When we're describing a surface, the direction vector will be normal to the surface. This is why I have to draw this down here under the document camera on the desk. Every time I draw it up here on the board, I keep walking into the normal vector coming out of the surface. I almost lost an eye that way. That's why when I draw little arrows, see how they're all rounded on the end? That's why I kept poking myself with these vectors. So I just started sanding off the tips. If you just do it and be even around, I'll take this. Well, that's why we just draw them and say this is the velocity, and then we just draw a long one for the velocity, then it doesn't even have to move. So here's what we want to do. We want to make sure that we can formulate this problem as a dot product. Because I have an expression for this vector V. The vector V is 0i plus 0j plus 1k. So it looks like if the vector V is 0i plus 0j plus 1k, if I want to do that route, so I got 0i, 0j, 1k, and I have the dot product with this area vector. The only thing that this tells us that the only component that has to be here is that last one. Is it 0 times whatever plus 0 times whatever plus 1 times, well, that must be 10. So that when we find the dot product, we end up with 10. because that matches our original description of 100% of the 1K flowing in the same direction as this normal vector. What does it make sense? Now we could put anything in these two, the I and J components. What's the only thing that makes sense to put in these I and J components? Must be 0 because of the simplified version. That's what things look like when we just flatten everything down. Don't worry about the X's, don't worry about the Y's. So this is us flattening out the rectangle. Mechanically, it would work out with any values there because of the 2 zeros in our V. But in the context of the problem, it makes sense to put zeros there because what we did was take this rectangle that was at a Z over Y slope of 4/3 and just flattened it down. So there's no X, 0 Y. Questions? Connecting some other things. Oh, wait, no. That's going to have to work out later. Actually, no, this is fine. If we look at this from the top, this flattened out one, we want to make sure that we capture all the things, what we know. Now, this is flattened out on the XY plane. So let's put the origin at that top part there. The Y over here. And Z is going up this way. We know that the area of this rectangle is 10. And I also want to highlight one of the things that I saw yesterday. As you can see on the board there, look through the past, look through time to look at the board from yesterday. So just take a moment. Everybody looking through time, look at the board from yesterday. I know we have to use like memory. I know some of you have to use memory. I'm just looking through time because I'm existing on a higher dimension than the rest of you. I'm just kidding. I'm just trying to rely on my memory. I actually can't remember if it was board 8 or board 9. I think it was 8. I think it was 8. There's a cross product there. And some other people had done some cross product. It wasn't just that one. That was just the first one I saw. So that's the one that's coming to mind right now. And the cross product was of these two vectors. Red. This vector 0, 0, oops, 2, 0, 0. This vector 2, 0, 0. And this vector along the y-axis now this one has to go all the way down. And remember this length is 5. So this would be 0, 5, 0. If we find the cross product of those vectors, we will have a vector perpendicular to the rectangle and with the area of that rectangle. So if we take 2, 0, 0 and find the cross product with 0, 5, 0, we will get a vector with a magnitude, that's the area, and direction that is perpendicular according to the right-hand rule. So that'll be 0, 0, 10. The cross product of two vectors will give you the area of a parallelogram, and the direction of that vector will be perpendicular to the parallelogram. And this 0, 0, 10 is also the vector that we just thought about. So good news, there were multiple ways to get at what we wanted in this problem. Bad news, there were multiple ways to get at what we wanted in this problem. The one that we have to know is all of them. It's math class, that's how it goes. You don't get to know one thing to get you to the answer because the answer is not important. You have to know all the things and how they're connected. All you have to know is everything. The true reward was the friends we made along the way. So we want to make sure that we can sort all these things out. We want to make sure that mechanically V dot A gives us the flux that we expect. We have to be able to, the problem is simplified to the point where we can just think our way to figure out what the flux should be. And we have to make sure all the mechanics build into that, because eventually we're not going to have a nice rectangle. We're going to have some continuously variable surface. And we're going to have to know that our calculations are going to give us what we want. That's why in Calc 2, when you're finding setting up volumes of solids of revolution, you start with things like cones and cylinders and spheres, because you revolve the rectangle around an axis and you find a cylinder. It's not about finding the volume of the cylinder or the volume of a cone or the volume of a sphere. We know those things already. It's about doing something where we get a result that we expect. We do all that work with the trigonometric substitution by rotating a semicircle around an axis to come up with 4/3 pi r cubed. The point was getting something that we expected. It's not knowing 4/3 pi r cubed. It's about using our new technique on something that we can verify by looking at it. Any questions? So when the question is like, oh, what's the best way to do this? The answer is yes. Now let's take this plate and put it at an angle and see what happens. So here's our simplified problem that we did not state yesterday. I'm going to look at the problem from the side because the problem is still in a simplified form. Yeah, so here the x-axis is coming directly out of the paper, and we're looking at the y-axis down here and the z-axis up here. In this picture, the velocity is still going vertically. The area is still 10. That's just the boring scalar area. What we care about now is from magnitude times cosine of angle. What we care about now is how much of the velocity is perpendicular . We know it's going to be less Because when the normal vector and the velocity vector are in the same direction, theta is 0, cosine of 0 is 1, and as cosine increases, cosine of theta decreases. So what we care about is the component of the velocity in the same direction. And the magnitude of the velocity normal to the rectangle will be the magnitude of v times the cosine of theta. Good question. Now we could try to figure out what the angle is, but we don't need to know the angle. I saw a couple groups calculating the angle. We actually don't need to know the angle because we care about the cosine of the angle. And the reason I picked this is I know that the angle is kind of messed up. It's like 36 point something, but the cosine of that angle is 3/5. Because the adjacent side is 3 and the hypotenuse is 5. That's why I did the 3, 4, 5. I wanted to see how many of you were in on teacher trips. So how is it? Adjacent is 3, hypotenuse is 5. Originally, I had super messed the problem up, and the angle was like, and the hypotenuse was like the square root. I'm like, oh wait, I need a 3, 4, 5. It's always 3, 4, 5. That's our default setting. So, in terms of magnitude of v times magnitude of a times a cosine of theta, that's really kind of going with the v over here. So I'm going to have the magnitude of v times the cosine of theta times the magnitude of the area vector. And for that, we just need the 10. Cosine is 3/5. And the magnitude of v is 1. And so our flux is 6. That makes sense. We knew that our flux was going to be less. Because at 100%, when the velocity was going perpendicular to the rectangle, when the velocity was in the same direction as the normal vector, that's our maximum. Cosine of 0 is equal to 1. And as soon as I start increasing that angle, I start decreasing the amount of velocity that's flowing perpendicular. We also have to have a vector that is normal to the rectangle with a magnitude of 10. Because that's what we had here, a vector normal to the rectangle with a magnitude of 10. So this vector has to be normal to the rectangle with a magnitude of 10. That's a good question. So, also, So we can think, we got to think about that. We got to think about what this vector here has to have. The magnitude has to be 10. And the direction needs to be normal. 0, 0, 10 is gonna would have given us a 10. That's when the angle between them is 0. So we got to think about that. In the previous problem, we just thought about that, but we also had this. We also used the cross product to get at that vector. What we saw from our simplified problem is that if we take the cross product of with the 2, 0, 0 and the 0, 5, 0, that gave us a vector that had a magnitude of 10 and the direction was normal to the surface, which is exactly what we are ordering here. We got to grab that vector. So I'm going to grab this vector here that goes from 0, 0, 0 to 0, 3, 4. So 0, 0, 0 to 0, 3, 4. That's going to be, don't change the x, 3, and then the 4. 0 on the x, 3 on the y, 4 on the z. So one way to get at that vector is to find this cross product. Here's my recommendation if you have not done so already. Think about what this vector should look like. We can get at that with slope. There's a reason that I put one of the edges of this rectangle right on the x-axis. So you only had to look at things from the side. And here the slope is 4/3, so the perpendicular slope is -3/4. Get that vector and make its magnitude 10, and that'll be the vector here. Think about geometry your way to this vector. Then verify that by cross-producting your way to that vector. And those of you who have assimilated cross-product, those are the same thing. I hope yes, but we might not all be there yet. You know what I mean? The point is that we put everything together. Not that we get the answer. I don't care that it was 6. I could have opened yesterday. It's like, oh, why is the flux 6? Right, but maybe I just want to do this. Come at this problem from all these different angles. Think about why these things happen. Think about what happened, what it would look like if I take this plate and move it all the way up and slam it into the XZ plane. What happens to the flux? If I take the plate and here's the velocity, and I take the plate and put it all the way up at the XZ plane. So here's my vector field. What happens to my flux? I just like, here, oh, careful, Ultraman style. Here we are at 0 degrees between normal vector of the plane and vector field. And then here we are, we're getting 60% of the vector flowing perpendicular. If I take the plate, keep its area at 10, and just move it all the way up into the XZ plane, how much of this vector field is flowing through that plate? 0. Why does that make sense in terms of the dot product magnitude, cosine? Why does that make sense?
Cosine 90.
Cosine of 90 is 0, and the angle between the normal vector and the vector field is 90. So the cosine of that is 0. None of this vector field is flowing through that surface. And if I go past that, what's going to happen to the values? Become negative. Because the orientation of this plate is downward and the vector field is flowing upward. Any questions? All right, that's it for today. I know I didn't do a cross product because I wanted to save all the fun of doing a cross product for y'all. It's pretty easy. There's a lot of zeros running around here, so be not afraid. That's it for today. I will see you all on tomorrow. Everybody have a good day and thanks for playing. All right, have a nice day.